In this lecture, we will discuss about deterministic finite automata or a DFA. What is a DFA? Formal definitions of DFA, graphical representation of a DFA, and transition tables. Basically, a DFA refers to deterministic finite automata. Before knowing about this, we must know what is a finite automata. We can say a finite automata is a machine, or we can say it is an abstract model where it can accept a language or decline a language by verification of valid words from a dictionary tool. This is called as a lexical analysis. A deterministic finite automata can be told when the machine reads an input string one symbol at a time. In DFAs, there is only one path for specific input from current state to next state. Formal definition of DFA. A DFA can be represented by using 5 tuple values, that is Q, sigma, delta, Q naught, and F. Discuss about them individually at a time. Now, what is Q? Q is number of finite states, or you can say a set of finite states. Sigma is a set of input symbols. Now, to read a language or to define a language, we require strings. And for strings, we require characters, sigma. So sigma is basically set of inputs. Delta, we can define delta as a finite states which receives an input, reaches to another finite state. This is called as a transition. It refers to the initial state. Basically, an initial state can be said as the state from which the reading of input symbols begins. And finally, the final state. Basically, a final state can be told where our input receiving stops and where our output generates. A DFA can consist number of final states. So we can say a final state is a subset of Q. So it cannot be more than Q. For example, we must design a language where all the strings begin with A. And the input strings, the input characters consists of A. You can say language may consist A, AA, triple A, and multiple A's, and many more. You just need to start with an A. Converting it into a finite number, this is where a DFA work comes out. Q naught is basically an initial state. We can name our states in any way. It can be A, it can be Q naught, it can be P naught. An initial state is represented through an arrow mark. Now, when we input naught and we give an input A to it, so it transitions to another state Q1. So the minimum possible string in the language is A. I have already received. So this state can be called as a final state. This is how a final state can be represented. But according to us, after A, there can be multiple A's. So we can self-loop the final state with an input symbol of A. Now let us check whether all the strings from our language are defined in this DFA. The minimum possible string is A, which we input it here and reach the final state. AA. Let us check for it. First would be A. You reach the final state. You give another A in the final state itself. From Q0 to Q1. Let's see whether all of 5 tuple values are discovered in this DFA. So first is Q, that is number of or the set of finite states. So the finite states over here is Q0 and Q1. The next is input symbols, which is given to us, that is A. Next, there is one initial state, that is Q0. State, that is Q1. And the transition table. Now, how do we represent a transition table for this particular DFA? Delta, we represent delta as finite state with input symbol reaches to another finite state. So delta, the input symbols, that is A, and the finite states. So this is the DFA we just designed for the language where all the strings begin with an A. The transition table for this goes as follows. Q0 receives A and reaches Q1. Q1 takes an input A and reaches Q1. So this can be a transition table. Let's discuss about it in various examples. There are certain rules to design a DFA. When the number of input symbols are more or equal to, so there must be minimum 2 transitions from each state. In DFAs, we come across dead states. Now, what are these dead states? Dead states are those which does not accept the strings from the language. For example, we are designing a DFA which accepts language with all the strings starting with A and ending with B. Where the input symbols are A and B. So first, let us discuss what can be a language for the certain question. So language can consist of AB, AAAB, ABB, and so on. Language should not contain A, B, BBA, or ABA, and so on. How can I define these languages? They have given a condition. The string must start with an A and end with a B. In between, there can be any arrangement. Now let's design a DFA for it. To begin with, I'll input a symbol A to my initial state and reach Q1. And now I will input the symbol B and reach Q2, where the possible string here can be AB, which is a minimum string in our language. So I'll call it a final state. But according to the pattern, there can be multiple A's and B's between A and B. So I can self-loop the state Q1 with the symbol A. And To avoid the strings such as A, B, A, I will self-loop the final state with B such that all the strings which are defined in this DFA will be ending with a B. And now, as we discussed earlier, according to the rules to design a DFA, when the input symbols are more than 2 or equal to 2, then each state must have minimum number of 2 transitions. Our DFA is not complete. State is lacking with 1 transition, and the final state is also lacking with 1 transition. So let's see about the final state first. In our pattern, between A and B, there can be multiple A's or multiple B's. So I'll give it a behind transition A such that it returns A to Q1, returns B to Q2, and we get a final product. And now, as we discussed about the dead states, our strings should not start with B. So at initial state, I will give a dead state transition of input symbol B and reach Q3, where it can give itself symbols of A and B. Now our DFA is complete. Let's check whether few of our strings in our language can be accessed. The string AB can be accessed. We are inputting A and then B. This can be done. Next, AAB. First, we are giving it an A. Then we remain at Q1 with another A. Then we give an input to Q2 or the final state B, where our final product is at Q2. The string AABB at Q0, we give A, we reach Q1, and now we give A and reach Q1 again. Now we give B and reach Q2. We remain at Q2 and give B. Our string is complete. Let's say we are designing a DFA that accepts language with strings ending with 2 zeros over the input symbols 0 and 1. So let's discuss about what strings are possible in our language. So our language can consist of 100, 00, 1000, 0100, and so on, where our minimum possible string can be a 00. But a language does not contain 001, 010, 011, and so on. So it is basically you give any input to the string from zeros and ones, but it must end with 2 zeros. Now let's design a DFA for that. To begin with, we'll check our least possible string, that is 00. That when you give an input of 0 to our initial state Q0, it reaches Q1. And then we give another 0 to reach Q2, that can be called as a final state. But this is not a complete DFA because the input symbols are 2, but the minimum possible transitions from each state is not 2. So to avoid all the strings which does not contain in the language, we can self-loop the initial state with an input symbol of 1 such that the strings beginning with 1 can be accepted, such that 100, 1100, 11100. Now from Q1, I will be giving another input 1 to Q0, such that we can remake these strings. Now we self-loop our final state with an input of 0, such that all the strings must end with a 0. And now, to avoid the ending to avoid strings which end with 1, I will give the input from the final state to the initial state with an input of 1. This can be called as a final state. Q0 has two transitions of 0 and 1, where Q1 also has a transition of 0 and 1. Q2, that is the final state, also have a transition of 0 and 1. The desires of a DFA is complete. All the 5 tuple values for the certain DFA, where Q is number of finite states, or the set of finite states, that is Q0, Q1, and Q2. The input symbols are 0 and 1. The initial state is Q0. The final state is Q2. The transition table for the following DFA is input symbols 0s and 1s, and the finite states Q0, Q1, and Q2. Where a final state Q0 takes the input 0 and goes to Q1. Q1 takes the input 0 and goes to the final state. Q2 takes the input 0 and remains on the final state. Coming to the input 1, Q0 takes the input 1 and remains at Q0. Q1 takes the input 1 and goes back to the initial state, whereas the Q2 also takes the input 1 and goes back to the initial state. This can be called as a transition table for the following. Well, let's say we are designing a DFA such that the language accepts three ending consecutive zeros. Over the input 0, 1. Now let's design a DFA for it. It's given that a language must consist of a string where the strings must end with 3 consecutive zeros. So the string can begin with any input and end with 3 consecutive zeros. So the minimum possible string can be 0, 0, 0. It can consist 1, 0, 0. It can consist double 1, 0, 0. It can consist 4 zeros and many more. The language should not contain the strings such as ending with 1, ending with a single 0, ending with 2 zeros, and so on. Now let's design a DFA for it. Let's begin with an initial state Q0, where it gives an input 0 to the state Q1. Now it takes an input of another 0 and reaches Q2. We require 3 consecutive zeros, So we give another 0 as an input to Q2 to reach Q3, where this can be called as a final. We need to check now that each state of a DFA must have minimum of 2 transitions. So the Q naught is having a 1 transition of 0. Q naught is having a 1 transition of zeros. So let's give a transition to itself. So let's give a transition to itself with an input of 1 such that strings beginning with 1 can be accepted. To avoid dead states, I will give input of 1 to each state and return to the initial state. And to make sure all the strings end with a 0, I give a self loop of input 0 at the final state. This can be called as a DFA because each state has minimum of 2 transitions. Now the 5 tuple values can be Q, that is a set of finite states, that is Q naught, Q1, Q2, and Q3. The input symbols are 0 and 1. The transitions can be known from a transition table. The initial state is Q naught. The final state is Q3. Now let's discuss a transition table for it. In our DFA, we give an input of 0 to the initial state and reach Q1. So Q naught receives 0 and reaches Q1. And now Q1 reaches Q2 with an input of 0. So Q1 reaches Q2 with the input of 0. Same way Q2 reaches to Q3 with an input of 0. Q3 remains on Q3 with an input of 0. So the input of 1, all states transitions to Q naught, that is the initial state for the input of 1. So design a DFA for the following strings, that is 101, 1011, 10110, 101101. That's it. So minimum possible string can be 101. Starting with 101, from our initial state, we give an input of 1 and reach Q1. And now we reach Q2 state with an input of 0. And now we reach the final state with an input of another 1. The minimum possible string is valid state to exclude all the strings beginning with 0. We also notice that there are no consecutive ones in the beginning, such as 110. So to avoid such situations, I will transition from Q1 to Q4 with an input of 1. And there are no consecutive zeros, such as 100. So I will transition from Q2 of input 0 to the dead state and self loop the final state with 1 and 0. Let's say we need to construct a DFA such that the language can accept even number of A's and B's starting with epsilon, that is the null string. over the input values A and B. Now, given that our language must consist of even number of A's and even number of B's in a string, and the null string can also be accepted. So minimum possible string is an epsilon. We can say AA, BB has even number of A's and B's. When we arrange them internally, AB, 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 BA, these can also be valid, so on. When epsilon is given as an input, our initial state will convert into a final state. That is, without receiving any input, we can call an initial state as a final state. For suppose we are giving an input of A and we reach another state, but we require even number of A's. So we return this A back to the final state. So the string AA can be possible. And now I'll say I'll give an input of B for the initial state and reach state Q2. But to maintain the even count, I am returning this back to the final state. So the string BB can be possible. For the arrangements of AABB, I will give an input at Q1 and return it back from the state Q3. And for the inputs BBAA, I will give transition from the Q2 state to the Q3 state with an input of A and return it back. Now let's check whether our strings are valid in this DFA or not. The strings ABAB, ABBA must be valid. From Q0, we give A to Q1. And now we give a B to Q3. We give another B to Q1 and we return a A to the final state. And our output is generated. For the string ABBA, for the string ABAB, we begin with Q0, we give input as A and we reach Q1. Now we give an input of B and we reach Q3. And now we give an input of another A and reach Q2. Now finally, we return another B and reach Q0, that is the final state. And the output is generated. So this DFA is a success. This can be a transition table for the following DFA, where Q1 takes A and reaches Q1. Q0 takes A and reaches Q1. Q0 takes B and reaches Q2. Q0 takes B and reaches Q2. Q1 takes A and reaches Q0. Q1 takes A and reaches Q0. Q1 takes B and reaches Q3. Q1 takes B and reaches Q3. Q2 takes A and reaches Q3. Q2 takes A and reaches Q3. Q2 takes B and reaches Q0. Q2 takes B and reaches Q0. And finally, Q3 takes A and reaches Q2. Q3 takes A and reaches Q2. Q3 takes B and reaches Q1. Q3 takes B and reaches Q1. This is all about deterministic finite automata or DFAs, where we discussed about what is a DFA, how they are used, the 5 tuples of a DFA, where DFA holds Q, sigma, delta, Q naught, and final state. Q1 refers to the set of finite states, sigma refers to the set of inputs, delta refers to the transition state as we saw earlier, Q naught refers to the initial state, and F refers to the final state. And then we discussed about the graphical representation. And then finally, the transition tables.